still open, so we won't be able to finish all the discussions today, but we expect that anyway. We'll finish it by tomorrow, by Thursday. Okay. So this week, of course, you looked at unitary matrices, different types of decompositions, so diagonalization, Schur decomposition, Jordan canonical forms, spectral theorems, singular value decompositions, all of these things, right? Okay, so since some of these calculations are also somewhat important, I'll also even discuss a few of the calculation questions just quickly by myself, just so you know what's going on. Okay. All right. Actually, yeah, before that, let's talk quickly about the project assignments. So each of you entered your group preferences, your top 4 preferences, and we were able to do an assignment such that each group got at least one of its top 3 choices. So thanks to TA Eric, we did it so that every group has at least one of its top 3 choices. Now we've created a Google Drive folder, so you can click on this link over here. It'll take you to a Google Drive, and every group has the corresponding folder created. So the expectation is that you will be periodically, on a weekly basis, updating this folder, updating this document. Okay, the expectations are not heavy. So the first week, which is week 5, which is this week, that is by tomorrow, I just expect a very short update, a short plan of action. So what do I mean by a plan of action? Well, so by tomorrow noon, so in the next like 20 hours or so, just put down what you hope to accomplish this semester, what you'll be reading, and so on. Okay, so I assume you've already taken at least a brief look at the materials. So just tell me what you want to do by the end of the semester. It's just a plan. Okay, it can change. It's not necessarily something that you'll be held to, but we'll start discussing it. Okay, by next week, I will expect you to write down a short report. Again, these reports are not expected to be long or very complicated or anything, but just like, you know, a page, 2 pages, something, just summarizing what you have done over the previous week. Okay, so for the first week, well, what are you planning on doing? For the second week, week 6, you'll write down what you have done so far. Over the course of the next few weeks, as you do more and more, maybe you write a short program. Well, put the program in this folder. Maybe you have some presentation. Well, put the presentation in this folder. Whatever materials you have, whatever you're reading, put them into the corresponding folder. Okay. So, and every week on Thursday at noon, I will start looking at your planning document. I will give comments on seeing what you have done so far and give you feedback. And then during the tutorial session, during the Thursday tutorial session, the TAs and I will go around and chat with you. Like if you need advice about something, we'll give you advice. We'll make some comments. We'll do whatever. Okay. So tentatively, I've also assigned for each TA between 4 and 5 groups. So each TA over here will be responsible for those corresponding groups over there. Okay. So that's how the projects will go. Okay. So let's begin by quick discussions about the content of this semester, of this week. So the first question, question 1, was to find essentially the square root of a particular unitary matrix, right? Of a particular matrix such that, to find four unitary matrices such that the square is equal to this. So, and the hint was that in particular, these complex numbers look like this, right? So there was a nice little solution over here, thanks to Zening. And I'm just going to, I mean, it's a simple enough solution, so I'm not going to invite Zening over, but I'm just going to point out what was done over here. So in this case, like the goal is to find a unitary matrix So, so what is a unitary matrix? A unitary matrix is something such that the transpose is its own conjugate, right? So in this case, given this particular matrix over here, given this particular matrix over here, 0, 1, -1, 0, one can diagonalize this matrix. One can the way to solve this thing is basically to, let me, where did I put the pen here? Okay. So given this matrix over here, given the matrix 0, 0, 1, -1, 0, I can diagonalize it as some P, D, P inverse, right? Now, suppose I say that this should be equal to U square. So suppose this should be like this. Then then what does that mean? It means I want to find something like, so if I want to find U over here, then I need to somehow take the square root of this quantity, right? What does that mean? I can take something like P times D to the half, and we'll talk about what this means, P inverse. What is D to the half? D to the half is whatever the diagonal entries were, lambda 1 to the half, lambda 2 to the half, okay? And for each of these lambda i's, we have choices. We can take plus minus lambda 1 to the half, plus minus lambda 2 to the half, right? So therefore, we end up with 4 square roots. We'll end up with 4 matrices such that when I take this P times D to the half times P inverse and then multiply it with itself, P inverse times D to the half times P, then these, P inverse. So then these will cancel. This D to the half times D to the half will give me D again, right? And I'll end up with U square. So the solutions will be of this form, right? So that was the idea in finding the square root of such a matrix, right? So that was the idea in question number 1. Okay, question number 2, there was a nice little solution over here. So question number 2 says find the orthogonal complement of this 2-dimensional space in this 4-dimensional space, right? So in this case, the solution, so that's basically like saying there is some vector space, R4, there is a vector space R4, so it's some 4-dimensional vector space, something like this. And there's a subspace spanned by 2 particular vectors. There's a subspace spanned by 2 particular vectors. What are those 2 vectors? Those 2 vectors are 1, 2, 1, 2. Let me just write them down. 1, 2, 1, 2 transpose, and 2, -1, -2, 1 transpose, right? So so there's a 2-dimensional space spanned by these 2 vectors, and we want to find the orthogonal complement. So we want to find another 2-dimensional space over here such that both the vectors here are perpendicular to both the vectors over here, right? And that they span such that these 2 vectors over here span the remaining part of the 4-dimensional space, right? That's what the orthogonal complement is. So if you think about it, that's basically like saying, if I take this as a matrix over here, then I'm just looking for a vector, let's call these vectors v1 and v2. I'm just looking for vectors v1 and v2 such that v1 is perpendicular to this and v2 is perpendicular to this. So really, I'm just looking for the null space of this matrix. If I call this matrix A over here, then the null space of this matrix A is precisely a 2-dimensional space which comprises of vectors which are perpendicular to, right, which have dot product 0 with the rows of this matrix over here, right? So based on this observation, the solution posted for question 2 by multiple people, Jian Long and others, basically did this, right? So so in this case, Patrick found it 1 by 1, or in this case he found one vector, then he found another vector, or there's a shortcut where, so let's see who did this, right. So in this case, J basically just directly took this matrix, asked for the null space, and automatically the span of these two vectors spans the orthogonal complement, right. So that's a quick way of doing it. All right. So as I announced, okay, so that's question number 2. Question number 3 and 4 actually have a common solution. So why is that? Because if you think about it, if I ask you to find the Schur complement, what am I doing? I'm asking you to find a matrix A. I'm asking you to write it in the form unitary upper triangular unitary dagger, right? And the Jordan canonical form, you can also write in this case as unitary and then a Jordan block and then unitary dagger. This Jordan block, the way it's defined, it's got these blocks over here, and these blocks are all upper triangular, and below it it's 0. So the Jordan form is automatically in the same form as the Schur canonical form, right? So the Schur canonical form is a special case of the Jordan canonical form. So really question 3 and question 4 were asking you to do the same thing, okay? There is a different way, a slightly more complicated way of computing the Schur complement, but we're not going to go into that. Let's just directly use the Jordan canonical form and try to find that. Now, unfortunately, the method I showed you in the videos, so I shot that video 2 years ago, and there's a mistake in the method of computing the Jordan canonical form in that video. I was hoping to correct it last night, but it's been a bit busy. I'm hoping now to correct it tonight, right? So anyway, with the TAs and I, we'll have an updated version of how to compute the Jordan canonical form. In particular, how to compute the generalized eigenvectors. The mistake was in how to compute the generalized eigenvectors. And Alder and a couple of other people had pointed out, and good job to them, had pointed out that there were mistakes in the method suggested on how to compute the generalized eigenvectors. Okay, so I need to correct that. So questions 3 and 4 we will discuss in more detail tomorrow during the tutorial. Okay, but I want to highlight the fact that there was a mistake in the class video on how to compute generalized eigenvectors. Okay, let's move on to question number 5. A quick discussion. So over here, the question was asking you to compute the singular value decomposition of a particular 4×3 matrix. Okay, so it's a rectangular matrix, it's not a square matrix. And singular value decompositions are probably one of the more useful things that you have studied this week, because they do show up in a variety of different engineering applications, right? So we were asking you to write this matrix as a unitary matrix times a diagonal matrix times a unitary matrix transpose, or alternatively as a linear combination of rank 1 matrices where these things correspond to left and right singular vectors and the sigma i's correspond to the singular values, right? And this is one of those questions that's pretty easy to do using maxima. So there was a nice little solution posted over here. In fact, I think several solutions. And I think Rui even posted the corresponding maxima code. So, but we can just directly see here how to do it. So, for example, Chanyu's solution. So, first of all, you enter the matrix. The rank of this matrix is 2, just as a sanity check. Then take the transpose of the matrix times the matrix and find the eigenvectors. So the eigenvectors are like this. And similarly, find the eigenvectors of C times the transpose of that matrix. So for the left singular vectors, you have to do this. For the right singular vectors, you have to do this, right? Because there are the left eigenvectors and the right eigenvectors, or the left singular vectors and the right singular vectors are respectively dimension 3 and dimension 4. So you do that. And then you put in the corresponding and then the diagonal matrix, the diagonal matrix in the middle corresponds to the singular values, which are the square roots of the eigenvalues over here. So in this case, the eigenvalues are 3 and 6. In this case, again, the eigenvalues are 3 and 6. So you have to take the square roots because the eigenvalues are the square of the singular values. You take the positive eigenvalues, right, and you put them over here. And then just as a sanity check, what what was done in this case was just to verify that the left singular values times the diagonal matrix times the transpose of the right singular vectors overall gives you the same matrix that we expect, right? Which is what we expect. Like in this case, notice that Maxima, Maxima is a pretty good software, but it isn't perfect. So in this case, Maxima failed to realize that square root 6 is the same as square root 2 times square root 3, right? So sometimes you do have to be a human and realize that, okay, you just have to manually simplify it. In this case, it may have been possible to ask Maxima to use something like ratsimp or some other commands over here to simplify this matrix over here. But sometimes you just have to check more carefully to see the form of the matrix over here. Okay. All right. So this was a quick summary of the first 5 questions, the first 5 calculation questions. Let's go on to the more conceptual questions, and I see there are some more updates I haven't seen yet. So question number 6 asked you to show that eigenvectors corresponding to distinct eigenvalues of a matrix are linearly independent. And the proof technique was quite similar to, was a slight generalization of theorem 1 in Kreyszig, chapter 8.4. Okay, so let's actually begin by looking at mistaken solution, right? So by the way, in this class, like even interesting mistakes are useful, right? Because they teach us something. So bonus points to Yurui as well for making interesting mistakes, right? So so in this case, what was the solution posted? So the solution posted was, well, let's multiply. So suppose so this was supposed to be a proof by contradiction. So suppose the eigenvectors are not linearly independent, then it's possible to write at least one of the eigenvectors as a linear combination of the other eigenvectors, right? And then this is a trick that often shows up in these problems. Multiply the whole equation by the matrix, right? Because what do we know about eigenvectors? Well, the matrix times an eigenvector gives us the same vector times a constant. So sometimes just multiplying by that matrix gives us some useful information, right? That's the first thing you should try in these eigenvalue, eigenvector questions. And then you end up with the same equation as before, but multiplied by the corresponding lambda i's on the left and the right, right? And then divide by the corresponding lambda I, and then compare coefficients, right? So in this step, now a couple of things to worry about. Well, firstly, lambda I might be equal to 0, in which case you may not be able to divide by lambda I, right? So that's one mistake. Another mistake is it's not possible, like in general, it is not possible to compare coefficients of 2 equations and say that these coefficients must be the same. Like if these entries over here, x1 is an eigenvector, x2 is an eigenvector, and so on, if these eigenvectors were linearly dependent, then you cannot directly compare coefficients. So as an example over here, suppose you have 3 vectors, 1, 0, 0, 1, and 1, 1. Clearly, these 3 vectors are linearly dependent, right? But you can check this equation is the same as this equation, right? But if I try to compare the coefficients of these vectors, if I try to compare the coefficients of 1, 0 with 1, 0 over here, then I would get the nonsense result saying 2 equal to 1, 2 equal to 1, 1 equal to 2. That doesn't make sense, right? So one has to be careful with these equations. You cannot necessarily compare coefficients when someone gives you the vectors. Now, if these vectors were linearly independent, if the vectors x1, x2, x3 on this side and x1, x2, x3 on this side were linearly independent, then indeed it would be possible to compare coefficients. Okay, that requires proof. But I invite you to think about why that would be the case. Okay, but anyway, so this question made a couple of interesting mistakes, and that's why I did want to highlight that. Okay, now there are multiple good, like well-written solutions over here. So let me highlight. So many of these are very nicely written. Let me point out Williams. By the way, I know I'm overly anal about this. but if things are sideways, at this point I'm getting old. I can't read like this for too long, right? So I do not even read things that are posted sideways. Okay, so please just make sure it's posted the right way. All right. So William's solution over here is very nicely written. So let's very quickly discuss this. So basically, it proceeds by induction. So if you have two eigenvectors, so suppose you just have two eigenvectors corresponding to two distinct solutions, two distinct eigenvalues, then the eigenvectors must be linearly independent. So this he proves. So this is the base case. He proves it fairly directly. So suppose there's some linear combination which gives you 0, then you have some alpha 1, then the first vector plus alpha 2 times the second eigenvector is equal to 0. Then the same trick, multiply by the matrix, and you'll still have the 0 vector on the right hand side. So that tells us that this alpha okay, so then you end up with this equation over here. Now you can subtract this equation from the original equation over here, and what that gives us is so in this case you have just two vectors. You have just two vectors. So since you have two vectors, and these two vectors are so you can scale by the corresponding alpha 1, and when you subtract it out, you get an equation like this. So alpha 2 times lambda 1 minus lambda 2 times this vector should be equal to 0. Now these two eigenvalues are distinct, so this cannot be equal to 0. This vector cannot be equal to 0. So therefore alpha 2 must be equal to 0, right? And similarly, you can prove that alpha 1 should also be equal to 0. So that's the base case. And then you assume that the same thing is true for k eigenvectors. If you have k eigenvectors, if you have k eigenvalues which are distinct, and then k eigenvectors corresponding to those must be linearly independent. So assume that, and then prove the same thing for the k plus 1th eigenvalue. So just prove it by induction. Okay. So I'm just going to let you read this one over here. The proof is very similar to the proof given in the textbook for general n by n matrices with n distinct eigenvalues, proving that they're all linearly independent. So this question was not that hard. I think it's okay. All right. So question number 7. This had 2 or 3 different interesting solutions over here. So let's dig into this one a little bit more. So in question number 7, so what was the question over here? Question number 7 defined this weird object called the matrix exponential, right? Which, if you think about it, is a very strange object. E is, of course, a scalar number, and then to the power of a matrix. At first sight, it looks very strange, right? But we can formally define it. We can formally define it just using this formula by saying, well, let's just use the same Taylor expansion for this object over here that we would use if it was a function in the variable x. Okay, so we'll take an infinite polynomial of this matrix and then call that the matrix exponential. So then we asked you to prove a couple of properties for this matrix exponential. Okay, so what properties did we ask you to prove? We asked you to prove that if x is Hermitian, then e to the x is also Hermitian. Okay, and Hermitian, like if it sounds scary, again, just think of it like a symmetric matrix. So if x is a real matrix, then Hermitian just means symmetric, right? So if you have a real symmetric matrix, then prove that the exponential of that real symmetric matrix is also symmetric. That's basically what this first point is asking you to prove, or a slight generalization of that in the complex setting, right? So again, there were multiple nice solutions for this one. So Chirui had a solution which was fine, but I mean it was a little bit clearer with some solutions down here. So let's go look at them down here. So let's see. Right. So here's a fact. Which let's see, who is this? Mayan got some ideas from Wikipedia. So firstly, the product of Hermitian matrices is still Hermitian. Why is that? So if I take the product of two matrices A and B, both of which are Hermitian, and I take the conjugate and then I take the transpose, then we already know because of how transposes work that AB transpose is B transpose A transpose. And then you have to check, but the conjugation operation, like if I take the conjugate of the product of two matrices, that's the same as taking the conjugate of one matrix times the conjugate of another matrix. Okay, you have to check this, but it's not too hard to verify. You can verify this yourself. And since both A and B are Hermitian matrices, so B transpose conjugate is B and A transpose conjugate is A. So therefore, this is equal to BA, right? So what this tells us is that the product of Hermitian matrices is Hermitian, because I can take the transpose conjugate and I get back the same matrix. It's equal to the same if AB is equal to BA. I'm sorry, if AB is equal to BA, and in this case, like if B is just a power of, like if A and B are powers of the same matrix, then indeed their AB is equal to BA, right? X cubed, for example, is x squared times x. It's also x times x squared, right? So therefore, in this case, I can write, I can decompose x cubed, for example, as x squared times x or x times x squared. So therefore, this condition is satisfied, and therefore it is Hermitian, right? You can also check that the sum of Hermitian matrices is Hermitian because if I take A plus B transpose conjugate, that's A transpose conjugate plus B transpose conjugate, which is A plus B, right? So this is true in general. So so in this case, this infinite polynomial over here is just the sum of powers of multiples of powers of the same Hermitian matrix, right? So powers of a Hermitian matrix are still Hermitian. So when I scale them by a multiple, they're still Hermitian, and then when I add them together, they're still Hermitian, right? So therefore, the matrix exponential of a Hermitian matrix is still Hermitian. Okay, so that's not too hard to prove. Interesting proof over here, the trickier part of the proof was to show that if x is skew Hermitian, then e to the x is unitary. Okay, so if x is skew Hermitian, that means, so in the case of a real matrix, if the transpose of the matrix is the negative of the matrix, then prove that the matrix exponential of such a matrix is a unitary matrix. Okay, and by the way, it can be shown that every unitary matrix can be written as a matrix exponential. Okay, so as a bonus point question, think about how to compute, how to find the underlying skew Hermitian matrix corresponding to any unitary matrix. Okay, and that's an interesting exercise for you to think about. So in this case, there are actually 2 or 3 different ideas. So let's look at those different ideas. Let's first look at a detailed solution involving a lot of calculation. Let's see if you can zoom in over here. Let's see. Okay, let's go down here. Save image, open image in new tab. Okay, good. We can zoom in. So let's see. In this case, okay. So suppose we have yeah. So suppose someone gives us a skew Hermitian matrix. So you've studied in your eigenvalues of a skew Hermitian matrix. So in one of the videos, we told you that the eigenvalues of a skew Hermitian matrix are all purely imaginary. Okay. In one of the videos, the same video where we showed you the spectral theorem, where we showed you that the eigenvalues of a Hermitian matrix are all purely real, the eigenvalues of a skew Hermitian matrix are all purely imaginary. Okay, that was also briefly mentioned in the same video. It's also there in your notes. Okay, and also the same video we showed you that skew Hermitian matrices are diagonalizable. Okay, so based on these two facts, then the proof is not too hard. So here's how one proof would go. So what can you do? You can say, okay, so my matrix X is diagonalizable because my matrix X is skew Hermitian. So I've already claimed that it's diagonalizable, and the diagonal entries are in this case they're all complex numbers. In this case, they're all purely imaginary numbers. They're purely imaginary numbers. So I can write them as some e to the iota a, where here these things are purely imaginary numbers. Okay, so now if I have a matrix where the diagonal entries are purely imaginary numbers, then the diagonal entries for this d over here, the diagonal entries for this d over here are, this should not be, yeah, okay, sorry, the diagonal entries here are purely imaginary numbers. So these ai's are real numbers times iota, where iota is the root of -1, right? So now my matrix exponential is given by this formula over here. Summation k goes from 0 to infinity, x to the power k by k factorial, which I can write like this. So p times d times p inverse to the power k by k factorial. Now, when I take the kth power here, the p inverse cancels out with the next p. So I'll basically end up with p times d to the k by k factorial p inverse, right? And then I can pull the summation inside. So I'm left with p times this summation over here times p inverse. So this is p times this diagonal matrix, where the diagonal entries are basically the same infinite summations of these purely imaginary numbers, and that's nothing but this exponential. So this is just the formula, by Euler's formula. This is just the exponent of e to the, this is the exponential of iota a11 all the way till exponential of iota a n, right? So therefore this quantity over here is so now the claim is that this must be a unitary matrix. So why is this a unitary matrix? Well, just take this matrix times its transpose. So if I take this matrix times its transpose, then the p inverse. So then I end up with p inverse times the, sorry, transpose conjugate. So I end up with p inverse times the transpose conjugate of this matrix, transpose conjugate of e to the iota a11 is e to the minus iota a11. Transpose conjugate of e to the iota a22 is e to the minus iota a22, and so on, times p, right? So when you work it out, then the p inverses cancel. This multiplied with its transpose conjugate gives me identity, and then the p inverse again multiply out give me identity. So basically, in this case, this matrix over here, you can verify just by direct calculation, is a unitary matrix over here. Okay, so that's a detailed way of calculating it. Here was a shortcut noticed by some people, which is also worth noting. So as Sky noted, that if x and y commute, then you can actually prove that the matrix exponentials satisfy this property, right? So the matrix exponential of x times the matrix exponential of y is equal to the matrix exponential of x plus y. This is true if and only if x and y commute. If and only if x times y is equal to y times x. Okay? So in this case, this actually requires a proof. The proof is not too hard. The proof is not too hard. It can be checked over here. We're not going to go into it over here, but the proof can be checked over here, or you can derive it fairly easily. But if this is the case, then you can use this identity over here and note that for a skew Hermitian matrix, if I take the matrix exponential of x, times the matrix exponential of X transpose conjugate, then I can just add together X and X transpose conjugate, which is going to give me the 0 matrix, which is going to be the identity matrix, and therefore e to the X is unitary, right? So this is a slicker way of proving it, but first you have to prove this property about matrix exponentials, that formula, which you're used to for real functions. But again, matrix exponentials are weird functions, so it's hard to prove them, prove such a formula in general, right? Some of you tried to directly, by brute force, try to work out things like e to the n times e to the m, and here you were having trouble with making it work out. And the problem is actually partly this: if n and m do not commute, then this formula will not work, right? So that's part of the problem. Part of the other part of the problem is just the way the summations work and so on. So it's an interesting attempt, right? Good job. But sometimes some methods work, other methods don't work, right? So it's worth trying out all these different methods. Okay, so that was question number 7. We have, let's see, 8 minutes left. Okay, let's see. So we can at least discuss question number 8, and then maybe we'll have to push question number 9 to the tutorial tomorrow as well. Okay. So question number 8. What was question number 8 trying to prove? So question number 8 was trying to prove a generalization of the spectral theorem. So the spectral theorem says that if you have a matrix that is Hermitian, then it is diagonalizable, right? Now, question number 8 says that it is unitarily diagonalizable. What is unitarily diagonalizable? It means that you can write it as a unitary matrix times a diagonal matrix times the transpose conjugate of that unitary matrix. Now, this theorem generalizes it in the largest way possible. So it asks you to show that in fact a matrix is unitarily diagonalizable if and only if it is a so-called normal matrix. Okay, what is the definition of a normal matrix? The definition of a normal matrix is that that matrix times its transpose conjugate is the same as the transpose conjugate times that matrix. Okay, so basically a matrix and its transpose conjugate commute. Okay? It doesn't matter in which order they show up. Okay, so and of course for a Hermitian matrix this is going to be true by definition, right? So or for a skew Hermitian matrix, for either of those matrices, those are special cases of normal matrices. But there are other matrices which are neither Hermitian nor skew Hermitian, but also satisfy this property. Okay, so how does the proof go? And there were a couple of hints telling you how to start thinking about it, and many of you had interesting ideas on how to do it, right? So let's look at some of your solutions over here. So okay, so suppose A is unitarily diagonalizable. So let's look at one direction. Then A can be written as some unitary matrix times a diagonal matrix times transpose conjugate, and the transpose conjugate of this matrix is then going to be this matrix times the transpose conjugate of the diagonal matrix times V dagger. So then we multiply them together, the V inverse, so V transpose conjugate is the same as V inverse because it's a unitary matrix. So V and V inverse will cancel out. The sigma dagger will multiply together, give us an identity matrix, and then again V dagger will give us an identity matrix. So in this case, the A, I'm sorry. So in this case, A dagger is going to be equal to A dagger A because sigma is diagonal over here. Okay, and by the way, I just made a mistake. It's not that sigma dagger is going to give us identity, right? Because some of the eigenvalues of this matrix may be 0. So there are no guarantees that this matrix has only non-zero eigenvalues, right? So if some of the eigenvalues are 0, then sigma sigma dagger may not give us the identity matrix, right? But what is still going to be true is that since sigma is diagonal, therefore the product of a diagonal matrix times another diagonal matrix is the same as if we reverse the order. So any two diagonal matrices always commute, right? If A and B are diagonal matrices, then A times B is equal to B times A, right? So that is why in this case, A times A dagger is equal to A dagger times A. By the way, so something like this is the missing part in question number 9. Okay, so if I have time, I'll quickly point out what's missing in the posted solution over here by Chaoyuan. It's a nice solution, but it's just missing one important part. Okay, the other important part over here in this question number 8 was to prove the other direction. Okay, so here now we have shown if the matrix is unitarily diagonalizable, then we have that sigma sigma star must be equal to sigma star sigma. That A star is equal to A star A. So we have that this matrix is normal. Okay, so unitarily diagonalizable means normal. Now we have to show the other way around. So suppose it's normal, we have to show that it's unitarily diagonalizable. So how do we do that? So suppose it's normal. So first of all, we start off with a Schur decomposition. So let's say A, you write in its Schur decomposition as U dagger TU, where T is an upper triangular matrix, and therefore A dagger will be written like this. So then you write A dagger like this, and A dagger A you can write like this. So now if these two matrices are equal, then that means that T dagger must be equal to T dagger T, right? Because these two matrices are going to be equal. So let me just write it down over here. These two matrices are going to be equal if and only if T dagger, oh, you can't see this, T dagger is equal to T dagger T U conjugate. Now, since these are unitary matrices, so they're invertible, so I can cancel this, So that tells me that this should be equal to this. And T is an upper triangular matrix, because that's how a Schur decomposition works, right? In a Schur decomposition, we say a matrix A is going to be equal to U dagger. That's what a Schur decomposition for a matrix is, where T is an upper triangular matrix. Okay, so now someone's telling us that a upper triangular matrix times its transpose conjugate is equal to the transpose conjugate times the same matrix. So I claim that implies that this matrix must be a diagonal matrix. So not only is it upper triangular, but in fact it must be diagonal. So above the diagonal and below the diagonal, it must be 0. That's what this thing is claiming over here. Okay, and how does the proof go? So let me very quickly just show you geometrically what the proofs and there were solutions posted over there. But geometrically, let me show you what that proof is saying. Okay, so suppose I say, suppose I look at T dagger is equal to T dagger T. Okay, so what is T? So T is maybe some upper triangular matrix. T dagger looks like this, right? T dagger over here looks like this, and T looks like this. Okay, so first on this side, what are we getting? When I do this multiplication, so this row dot product, so this is 0. Remember, this is 0, and in this case, this is 0. This is 0. So when I do this dot product with the first column over here, then I end up with just the square of this element over here, right? I end up with just the square of this diagonal element over here. Whereas when I do this row dot product with this column, I'm getting the norm square of this full vector over here, right? So what that must be, so therefore what must be true is that all the other elements over here must be equal to 0, right? Because here I have the full norm square, whereas here I just have the first element over here, right? And similarly, you can look at the second element, multiply it this way, and check right? And again, you'll find that other elements are going to be 0 and so on. Okay, so basically that's what the proof shown in the proof shown in some of these proofs over here are trying to do. Okay, Galaxy here had a nice diagram saying basically the same thing over here. Okay, so nice little proof. Okay, we're basically out of time. Question number 9, there was a nice little solution, which is which is missing a particular step. So we'll hopefully discuss this tomorrow and also clean up the gaps over there. Okay. Yeah, today I just wanted to make sure we get through some important discussions. So I did not do the usual thing of inviting students over. Okay, we'll do more of that next week. So, but this week we are done with this. Okay, all right. Class is over. Thank you for paying attention. And tutorial tomorrow. Remember, so reminder. Remember to post your weekly update by noon tomorrow. Okay, nothing complicated. Just to get started with your project. So please post an update tomorrow.